All right, there we go. Yeah, so this idea comes down to what is the type of the reference variable and what is the type of the actual object. Now, all the behavior an object is going to have depends on what the type of that object is. It's not what the reference variable is. This is an important distinction, and we'll see what I mean as we go. So polymorphism is the idea that behavior can change depending on the type of the object. Well, it's not really that the behavior is changing, but when you have a reference variable of type stack, and you have an actual object, an instance of a stack that's an array stack or a linked stack, you know, when I call push, it's going to depend, like how that push works depends on what the actual type of that push, of that stack is. So the reference variable is for something of type stack, yet it can reference an object of type array stack or linked stack. This is because array stack is a stack, and similarly linked stack is also a stack. But it's not possible to do something like that. I can't make an array stack reference variable reference a linked stack. That's no good because a linked stack is not an array stack, and vice versa. So the reference variable is more general than the actual type of the actual instance. So note, the data, both my stack and O reference the same type. So here we go. Here's an example. Right? I have an array, or pardon me, I have a stack called my stack. That's a reference variable. And that's referencing a linked stack object. And I created another reference variable called O. That's of type object. Now everything is an object, like it or not. So I can have a reference variable of type object reference that same thing that the stack reference variable references, that particular linked stack that's created. The reference variable type can change, but the actual type of the object itself remains the same. It doesn't matter if a stack reference variable is referencing the linked stack or the object reference variable is referencing the linked stack. It's always a linked stack. That doesn't change. All right. So, for example, imagine I ran this code. And I ask you, like, let me hit pause on this. If you look at this line of code right here, what type of stack am I making on that line of code? It's not a trick question. A linked stack. And the reason we know is it says linked stack right there. In fact, we know before I even hit run, I know what the type is going to be. It's going to be a linked stack because it explicitly says it there. But imagine code that looked like this. And I ask you, based on this, what is the type of the stack that the reference variable my stack references? What's the type? Can you answer that question? Take a moment, look at the code, make sure it makes sense. Imagine random number is a value that gets determined by calling some function in Java saying give me a random number between 0 and 100 or something. So what's the type? It's not really a trick question. It kind of is, I suppose.
An array stack or a linked stack 50% of the time.
Yeah, we don't know. At least right now, we don't know. It's going to be one of those two. It's either going to be a linked stack or an array stack, but I don't know before I hit run, like I did before. I can only determine this at runtime. because it'll depend on what the value of random number is. So when I call, like print out my stack, it's going to call the toString, right? So whose toString is it going to be? Is it going to be the linked stack or the array stacks? Well, we don't know. Connecting a call of a method. So the method call, like look at lines 7, 8, or 8, 9, and 10. They're calling push. Connecting a call of a method to the actual implementation of that method is something called binding. Sometimes we know before we hit run, right? Like here, if I said my stack.push after this, I know it's going to call the push from the linked stack class. But here, I don't know. Is it going to be the push from the linked stack or is it going to be the push from the array stack? I don't know which version it's going to be. Now, the upside here is because they're both stacks and they both implemented the stack interface, I know that both implementations have a push. It's just I don't know right now which version it's going to be. If we know at compile time, this is before we hit run, we have what we call static binding. Java can go like, yeah, okay, it's going to call this method because the code's very clear. But sometimes we have something called dynamic binding, which is what would happen here. It doesn't know until it's running. Because either line 3 or line 5 is going to run. I don't know at compile time. I'm not going to know until runtime. So Java can't know which version of push or toString, etc. to call until it's running, which is kind of interesting. But it's all okay because we've got a stack, and the stacks must have push, right? It must. So it knows it's safe to call push. It doesn't know which one it's going to have to call yet until it runs. By the way, here's an interesting thing. There's a couple of ways to do this, but you can actually ask a reference variable what the type of the object is that it's referencing. So you can actually ask. And this, I believe this is actually used in several of the equals methods that we use. You can ask a reference variable that's referencing some instance of an object. You can ask it, hey, what's your class? And it would tell you a linked stack or an array stack, which is good. That's great. Anyways, that's the idea of polymorphism, which is kind of cool. That's one of the ideas of polymorphisms. It's a much bigger idea than just this, of course, but just to scratch the surface. Any questions about this idea? No, we're all good? Okie dokie. All right. Going back to the bag. Because we started talking about bags, and in the bags we had we talked about a general bag, but then we had a sorted bag and an indexed bag. Two different types. And this is where I had talked a little bit about inheritance. A sorted bag is a bag. A indexed bag is a bag. They're both bags. There's going to be some common functionality between the two types, but each specific type is going to have unique functionality to itself. So some of it's going to be similar, some of it's not. So we talked about the functionality that we would want to include, like the signatures we would want to include in the interfaces. We started with the bag interface, where we had a couple of methods that we knew we would want to implement. Then we wrote our sorted bag interface the only real funny thing here was that we had that restriction on the generic type. The type had to be actually comparable. That just is a fancy way of saying there must be some defined ordering for the objects you're trying to add to the sorted bag. Otherwise, how would you do it? But we also included specific methods that we would care about for a sorted bag. Like give me the first, give me the minimum, give me the maximum. And similarly with an indexed bag, we had specific functionality we would want for our indexed bag implementations on top of what we got for free from the bag. Because both the sorted bag and the indexed bag inherited from the bag. So we're going to build an array-based implementation of bags. We could do this with the linked one, but we're going to do an array one here. If you're wondering why the array one and not the linked one, because. Really no reason other than we're going to do it with the array. So we're going to make an array-based implementation. So the array is going to be the container. So we'll have an array, a field that has an array in the implementations. And there's going to be some other stuff depending on the type maybe, but we'll see. So similar to the stack and the queue-based implementation. Unlike the queue though, remember with the queue we had that issue with the array implementation. We had that like circle queue. Because we had that whole issue of we always remove from the front, and we always want the index 0. You of course remember we had the 3 implementations of the queue, right? The array queue. There was the first idea where we shuffled everything down. The second idea where we just kind of didn't shuffle things down, but we remembered where the front was. And then the third idea, which was that circular array idea. We don't need to worry about the circular array idea here. Because with a bag, when I remove something, for a sorted bag, we might be removing the maximum, we might be removing the minimum, but we also might be removing a specific element. If we go look at the interface, we might be removing a specific element. The point I'm making is where in that array I'm going to be removing from is arbitrary. The queue, it was always from the front. But with the bag, it could be the front, it could be the end, it could be in the middle, it could be anywhere. So this whole circular array idea, the advantage there was knowing that we were always pulling from the front, dequeuing from the front, so we did that special update there to make it constant time. But if I have an array, imagine I'm removing from the middle, some arbitrary spot in the middle. I'm going to create like a hole in my contiguous data, right? And I don't know about you, I can't really think of any clever bookkeeping like a circle array to deal with those gaps. Anyone have an idea what we could do to address those gaps? It's not a trick question. You should have an idea. What's the simplest way you can eliminate the gap?
Make the one on the other side of the gap reference.
Just move them down?
Yeah, I guess.
Yeah, I'd say just move them down. It sucks, but the reason I say it sucks is because remember in the lab we built that rudimentary array queue, right? Where you would always have to shuffle everything down. The disadvantage of that was, the computational complexity. It was always linear. Every DQ was linear, so we had to shuffle everything down. But the circular queue made it so the DQs were constant. Great. But with the queue, or with the bag, we're not using a circle queue, and we're kind of stuck because we could be removing anything from anywhere. So as soon as we introduce a gap, we got to close that gap. We're going to have to shuffle things down, no matter what. And if we're shuffling things down, remember, I might be shuffling things down to index 0, maybe at the very end, so nothing shuffles just anywhere in between. What's the computational complexity of shuffling down an arbitrary position in that array? Who can tell me? Why?
Because you have to move everything in the array.
Yeah. Yeah, because we can think of best case scenario, I remove the thing at the end. Nothing needs to be shuffled down. Great. Worst case scenario, I remove the thing at the very beginning. Kind of like that idea 1 of the queue, the array queue. Everything's got to be moved down. And then for every time it's there, it's at the other end. For every time it's the second from the front, it's the second from the last. On average, we're going to be removing something somewhere in like the middle. Either way, it's linear time. There's no way we can kind of hack this to come up with a better solution, easily at least. So we don't need to worry about all that extra fancy bookkeeping we did with the array cube. For better or worse, we'll have a simpler implementation, but it requires a little bit more overhead for every time we remove something. Similarly, every time we add something, though, imagine I have a sorted bag. With a cube, I always added to the end. Nothing needed to move. I just added to the end and updated the size, right? But if I have a sorted bag, I'm not always adding to the end. Same with the index bag. I could be adding to index 7, any arbitrary spot in that bag. Well, what if there's something already in index 7? What do I got to do? It's not a trick question. What do I do?
Push everything down from index 7.
Yeah, make room. Put the thing at index n to n plus 1. N minus 1 to n, n minus 2 to n minus 1, and so on until I open up room and I can put something in there. Which then means in arbitrary add, what's the computational complexity of an arbitrary add now? Look, if you're not answering because you're tired and whatever, that's one thing. If you're not answering because you don't know, we're in trouble. Let's try that again. Based on what was just talked about, making room. What's the computational complexity of an arbitrary add to these bags? Why?
Because you scale up everything.
Yeah. Imagine I have to add something in the beginning. I got to move everything down 1 to make room at the very beginning. To open up the spot at index 0, everything needs to move down 1 just so I can add something there. So again, with the cube and with the stack, adding always happened at one end. There was no it was always constant time, but again with the bag, it's more general, which is great on one hand, but with the ability to add and remove things from arbitrary spots in that array, or in the bag, the computational complexity is worse. There's no silver bullet here. There's no free lunch. You win some, you lose some. A stack, really simple, can't do much with it, but it's fast. A bag, way more general. You can add and remove things wherever you want. But adding and removing from those things require a lot more work than the stack did. Similarly with a cube, right? So with more generalness, usually comes more complexity with implementation and more complexity with, well, how much work it takes to do everything. Not always, but often we see this happening. All right. Unlike the queue, the front will always be index 0. With bags, adding and removing can happen anywhere. Adding to the middle would require a linear time operation to move everything down 1 spot to make space. Removing from the middle would require constant or linear time to move everything down to close the space created from the removal. So these are linear now, where before we were so focused on trying to get them to be constant time for the stacks and the queues. We're kind of stuck here. They're going to be linear, for better or worse. That said, linear is really not all that bad. If you can have constant time over linear, yeah, do it. But at the end of the day, a linear time operation isn't too bad. Expand capacity is going to be required. It's an array. We might run out of room. But we've done that. We've dealt with that a bunch of times. Just make a bigger array. It's going to be a much simpler version than the queue because the front's always index 0. And the functionality of a bag, regardless of whichever version it is going to require an add, a remove, contains, count, is empty, size, and this iterator thing, which is yet to really be talked about. So those are the things that we're going to want to implement regardless of which bag we're implementing. But let's start actually implementing an array index bag. We won't start with the sorted bag because it's a little bit more complex. We'll start with the array index bag. So in addition to everything that a bag can do, we want our array index bag to also be able to add something to a specific index, remove something from a specific index, set something at a specific index. So unlike add, where add made room for something, everything moved down, we inserted something, set would be to go and change whatever was at that spot. Get the thing at a specific index, and then index of, which is a nice way to just tell me, okay, look for some object and tell me the index that I can find it in. Often, if your collection has allows multiple copies of a given element, this will always, typically, depending on the underlying container, typically it returns like the first occurrence of that thing, for example. Now, I will say, I'm not going to go over every single one of these implementations. That's for you to do. You can go download the code, look through it, understand it, great. But we're going to hit some of the big ones here. So let's start talking a little bit about the implementation of an array index bag. This right here, nothing in here should surprise you. The only thing here that's kind of new is this whole Java util iterator that we're importing. Everything else we've kind of done. Actually, I also don't, did we do? Yeah, we did use arrays before. So here's two constructors. This looks basically like every constructor the two constructors we've seen for all array-based implementations we've used so far in the course. One default constructor, and then one that creates an array of some specified size. And of course, it's got that funny casting thing we have to do because Java. Yeah, note the import iterator and the implementation of iterator, though we haven't implemented iterator yet. Iterators are used for iterating over a collection. More on this later. Private methods. So here's two private methods I added to my implementation. I didn't need to implement these, but they make things a little easier, I think. So these are methods that the interface does not say this class is supposed to have. These are methods I'm adding to my class because it's going to make implementing the other methods a little easier. I've got one called shift left and one called shift right. Shift left is used to move elements down in an array. Meaning, if I've got a gap, I'm going to have to shift elements down, one at a time. That's the whole eliminating a gap after a remove, for example. And then there's shift right, that's move everything down one to make room. To create a gap, basically. And they actually allow me to, I've written it so it's got a parameter start where I can specify where I want to start making room. So in shift left, start would be, I guess, where the hole is. And that moves everyone down one. Be mindful of it loops to rear -1. This is a very common mistake new programmers make. Take a moment. Really, I'll give you a couple seconds here to look at this code to make sure it actually makes sense to you. Because this type of algorithm is actually, this algorithm is very common. And I want to make sure you have a chance to look at this code and make sense of it. And if you have any questions, we can talk about it. All right, let's talk about this one. Let's say shift left. Let's say I eliminated B. So this is index 0, 1, 2, 3. I'm going to call shift left with start being 1. All right, I starts at 1. Well, I is less than rear minus 1. In this case, rear is going to be the length of the array. It just so happens that the array is at capacity before the remove. So let's look at what the code says. So rear is 4. Because it's the length 4, right? It's just, if I were to add again, assuming there was something here, it would have to call expand capacity, of course. But we're just so happen to be at capacity. What does the code say? All right, bag at index I, which starts at 1, you are equal to what's in I plus 1. Well, that's C, right? This is I plus 1, right? So copy C down, great. We're done that iteration of the loop, increment I, start is now 2. Okay, go to index 2 and put in it what's in index 2 plus 1. Well, that's 3. All right, put D here. Okay, I is now 3. Now is 3 less than 4 minus 1? No. So it would stop here. And then immediately you see rear minus 1 equals null. Well, that then goes here and just gets rid of it. Technically not really necessary, but I'm a big believer in, if the data doesn't mean anything, just get rid of it. So you don't have any funny issues that could arise later. Very defensive. Imagine for a second we still had a D here. And imagine I didn't loop to rear minus 1. If I looped all the way to rear, okay? Rear, I is now 3. Copy into 3, what's at index 3 plus 1? Which is 4. What's in the array at index 4? Who said nothing? Nothing? What is this?
It doesn't exist.
It doesn't exist? Array index out of bounds. That's what we have. All variations of nothing, what? It doesn't exist. Correct. It doesn't exist. So, you gotta think. Each time through the loop, usually if we're iterating over an array, and we want to put our finger on each element in the array, and the array is length n, I want my loop to run n times. But that's not really what's happening here. Each time through the array, I'm not putting my finger on each thing. No. Each time through the array, I'm putting my fingers on adjacent pairs. The number of adjacent pairs I have is always like length minus 1. Right? Because I'm not putting my finger on each thing. I'm not going 1, 2, 3, 4. I'm going 1, 2, 3. So keep that in mind. Then we have shift right, which is a very similar thing. Just work through it if you want to make sure it really makes sense. But it's like the reverse of this. Close or open. Make room. Now, an interesting thing to note here, and I think I also, this method assumes there's room in the array to facilitate shifting. Imagine I had a case like if I were to do this and I were to call shift right like this, I would actually have an issue, right? Because it starts at rear, and rear is index 4, but there is no 4. So I would have to be very careful when I call shift right. The simplest thing here is only ever call shift right after an expand capacity, if an expand capacity was needed. So that's the easy solution. And we'll see an example. I think I show an example of that code. If not, it's in the code I give you. Okay, iterator methods. So, iterators are the focus of another topic. I'm only going to briefly talk about them here. And the reason I'm talking about them here is we're going to make good uses of them. And we could have made good use of iterators throughout the course so far, but I didn't want to throw you too much into the deep end. So iterators are a way to give you a common, consistent way of iterating over a collection, regardless of the underlying container. Because right now, if I told you to loop over the contents of an array, how would you do it? Probably a for loop, right? You'd probably use a for loop, go to the end of the array, or however many things you care about in the array. With a linked structure, you probably wouldn't use a for loop. You'd probably use like a while loop. While some node reference is not null, go to the next one, you know. But that's very different. An iterator is a way to kind of consolidate those ideas to make it so the way you iterate over, and iterate, if that word's unclear to you, iterate means like iterating. 1, 2, 3, like one at a time. So iterators make an easy way to iterate over a collection. All this method does is create what I've called here an array iterator and return it. What an array iterator is exactly will be discussed in the next topic. But the sneak peek is iterators make it so I don't care what the underlying collection is. The way I can iterate over that collection is the same regardless of the underlying collection. It's really nice. You'll see. Okay, add. Okay, I have two adds. There's the add I inherited for free from the bag. And if we go back and look at the interface for the bag, the add that we got is an add that just takes an element. But then the array, or pardon me, the index bag had an additional add. One where it takes an element, but it also takes an index where I want that element to go. So I need to implement both adds. I must. Because effectively, the index bag has two adds in the interface. One it had explicitly, one it inherited. And everything in that interface has to be implemented in order for Java to even deal with this. So I have to implement both adds. This then begs the question, like, okay, look, the add for, when I say add an element, add something to a specific index, that one's pretty straightforward, right? You specify the index, that's where you want the thing to go. What should the add do that doesn't take an index? What should we do? Really, this is up to us. What we should do, in my opinion, is something that makes sense, but really it's up to us. The one where we specify the index, that one's painfully obvious. But where should we add things if we just call the add without specifying an index? And to me, it makes sense to just basically make that the append. Just add to the end. If you don't specify an index, you're appending it to the end. Does that seem reasonable? I think it's reasonable. But if for whatever reason you're thinking to yourself, no. If you ever, no, it should add it to the front. If you think so, for your implementation, not for this course, but for when you need to do it, sure, do whatever you want. But to me, it just makes sense to add it to the end. Now you'll notice this add here delegates. The add method that doesn't take an index, the one from the bag interface, I didn't actually write that code at all. I didn't describe what that does. I simply delegated to the other add. There's two adds that I'm writing. And Java resolves the ambiguity. Well, there is no ambiguity here. But we could point to be like, well, you have two add methods. How does it know which one to call? Well, it knows which one to call based on the arguments, the parameters you give it, right? The parameters it gets. If it takes a single thing of type T, okay, it's calling the add method that takes a single thing of type T. If it's calling add that takes an integer and something of type T, well, it knows which ones it's going to take. So I just delegate to this add by just giving it the rear index, which is always the end, right? Rear is the next available spot, like the queue in the stack. So that's kind of cool, right? No sense rewriting everything, just delegate it by specifying the index in there. I think that's pretty cool. And in fact, this idea of like delegating is going to be used frequently as we go. But any questions about that whole delegation thing that I'm doing there? All it does is if you call add, where you give it a single element, that add just calls the other add, but it just shoves the rear index in front of it before it does. That's all that's happening. And if you're looking for it to be more complex, don't. Remember, computer scientists are lazy and stupid. If it's complicated, we can't do it. Now, the other add. Okay, this add takes an integer, that's the index we want to add it, and an element. Now, we actually have to check. Raise your hand if you ever got an array index out of bounds. Of course you did. Curses, right? Well, actually now you're defining a collection where you get to tell someone that now your index is out of bounds. So now you get to be the one that gets to throw the exception. So there you go. Right? So now, if anyone ever calls this method with an integer less than 0 or greater than the size, raise an exception. Throw that exception, the array index out of bounds. And the message is the index. That should give them enough details. Now, you'll actually notice here, there's actually an interesting little edge case here. When the index is size, it's actually valid. Let me put it this way. With an array, if I gave you an array of size 10, there is no index 10, right? But here, if I said add something at index 10, there is no index 10. But that would be like appended. So it's a little different than the array one, because if you specified effectively what the length of that array is as an index for the array, you'd have an array index out of bounds. Here, if you specified that like capacity mark, it's not actually out of bounds yet, because that index is valid, because it would just be adding to the end. Right? Does that nuance make sense? I think it's kind of neat to point out. There's a comment there just to appease any confused programmers. Size is valid, it's just the append. Here's what I mean. Here is an array. If I said anything at index 4, it's array index out of bounds. Imagine this is an array. This is my array index peg. There's four things in it. I really don't know how long this array is. Right? Let's make it like dotted. Because I kind of hide the fact that any expand capacity needs to happen. But if I said add to index B, for example, everything needs to shuffle down 1, and I add it there. If I add to index 4, well, that doesn't really exist yet, but that's fine, because index 4 would be valid, that's just appending. If I said index 5, well, yeah, okay, now we're in trouble. But with the array, anything at index 4, no good, it doesn't exist. Just an interesting point. Okay, now, here. This is if size is equal to the bag.length. This is the case where my array is run out of room. Bag is the field, that's the array. But you'll notice every time before, what private method did we always write and we always call whenever our array ran out of room? What method? This is not a trick question. I just mentioned it a moment ago. Expand capacity. Now here's the thing. We wrote that. And the reason we wrote it before was because it's important for us to understand what the hell's going on. So we wrote the code. But we're far enough along that I can tell you a secret. No programmer in their right mind would write that code. Because there exists a function already available to you in the arrays class called copyOf. That will just automatically do expand capacity for you. So you call arrays copyOf, you give it the array you want to make a copy of, you give it the length of the array that you want to be created, and that returns the new array. So here, I said make a copy of bag, which has size 10, let's say. But I want your new array to be size 20. Put everything from index 0 to 9 over from bag, and return it. So that's what that line of code does now. From now on, you're allowed to do this. Don't write expand capacity. Okay, so what are the cases we've caught? We've done, okay, raise the exception if we run out of room, or pardon me, if they specify an invalid index, expand the capacity if we ever run out of room in our array. Otherwise, what do? Well, now we know everything's fine. Whether I expanded capacity or not is irrelevant. Here's what I do. I shift right, starting at the index that I'm adding to. Remember, shift right is open up space. And notice that I'm doing the shift right after any expand capacity if it was required, meaning I know that it's safe to do so. So shift right, make room, add the thing to the index. That index is going to be empty now because we copied everything down. And then increase rear because, well, we just moved rear down. And then if it's successful, return true. And this will only ever return true because it can't fail. That's add. Now, I want to take a moment to emphasize. When I started describing this add, I'm willing to bet a number of you in here were thinking, okay, it's clearly more complex than the adds we did before. The adds we did before always added to one end. It was safe, it was fine, it was easy peasy. Expand capacity was still a thing, fine. But you knew that this add was coming, and it was going to get more complicated. But I'm willing to bet that the inclusion of the private method shift right and abstracting that functionality out to its own function, own method, pardon me, suddenly makes this really not too bad. Think about the algorithm at the abstract level that this code is presented at. Is it a valid index? Do we have to expand capacity? Yes or no? If you do, do it. If you don't, whatever. Shift right. That means make room. Make room such that the thing at index is empty. Add the thing to the index. Increase size, return true. At that abstraction level, that, I think, is quite simple. And I think it's kind of like elegant, really. But the trick is to abstract that whole shifting right thing. If you didn't take a moment to write that shift right private method, you would effectively have that method. You could copy and paste that code from the shift right method into this function right, in this method right here. And that's entirely fine. But suddenly, the code, I don't know. The point I'm trying to make here is by abstracting some functionality out to its own method with a good name, maybe shift right could be a better name. Maybe it could be like make space. Maybe that would be a better name. And the shift left could be remove space. Oh. But nevertheless, by extracting that functionality out and having a method to do that kind of annoying part, which when you abstracted that annoying part out, I'm willing to bet that no one looked at this method right here and thought to themselves, oh man, that's so complicated. I really don't think anyone looked at that code and thought that. But when thinking of this along with the add together, it is a little bit more complicated, isn't it? If you think like, oh, that add needs to make room. But by simply extracting it out, putting it in its own method, it's really not too bad, and then calling it, it makes this add method so nice and clean. The emphasis here is on taking the time to think about how you're writing your code. Private helper methods, you might, even if you only ever call that helper method, that private method once. Because a lot of times, the whole motivation for making a function or a method is like reusability, right? You write it once, you can call it a million times. But you might think to yourself, I only really need to call it once though. So is there really a point to extracting it out? Well, maybe, maybe not. Here, I'd say, yeah, I like it. Because it makes this method so much easier, so much cleaner, so much clearer. Does that make sense? I hope it kind of does. A lot of new programmers focus so much on just getting the code working. And of course that's important. That's only a part of it. Getting the code working, making sure it's correct, your tests. But also taking the time to write good quality code is very important. Far more important than a lot of new programmers really give it credit. They joke. There are 3 hard problems in computer science. 3 hard problems. Does anyone know what they are? There's 3 hard problems. 1, caching. Yeah, it's tough. Don't worry about it. 2, naming things. And we can maybe generalize that to naming the function method as well, right? Naming things. And 3, off by 1 errors. And the off by 1 error, an example of that would be like this, right? Where you've got like the -1. That would have been an off by 1 error. And of course, that's part of the joke. That's the 2 hard problems. There's 3 of them. One of them's off by 1 error. Come on, laugh. There you go. There you are. But that is the same. If you find yourself sitting going like, what should I name this variable? You're on the right track. If you find yourself saying, what order should I put this code? Should I put that line of code here or that line of code there, or should I flip them? It doesn't matter, but what makes more sense? If you're thinking like that, you're on the right track in terms of being by considering what your code looks like. All right, I'll see some of you tomorrow and the rest of you Friday.